Hey guys, my name is Jackson Jones, and this is my Lab 5, which is magnetic braking with Faraday. For an introduction, the purpose of the lab was to collect data on a magnet falling through an aluminum tube and to observe and apply Faraday's law and to model the magnet/tube interactions and compare that data with actual data. Some fundamental principles we need are that our Faraday's law, which says that the EMF equals your negative change of flux, the Biot-Savart law, which we used in Lab 3, Ohm's law, and then the magnetic force on a loop. Your system is the tube and the magnet, and your surroundings are everything else. For the experimental results, I found that the experimental time using the videos was 1.47 seconds averaged out, and I think that time used or found for the computational data was about 1.41. I forgot to include that in there. Some assumptions are that air resistance acting on the falling magnet is negligible, and that the only two forces present are the force of gravity and the magnetic force from the aluminum tube. The experimental procedure itself. First, I found what the north pole of the magnet, or what the magnet was using the magnetometer app on the phone. And then we set a camera to record as the magnet was dropped through the aluminum tube 5 times. And then the time it took for the magnet to fall through the tube was found each time and averaged out. For some measurements and data, so as you could see, the average of those 5 times, it ended up being like 1.471. And some measurements, so the total length of the tube was 0.3 meters, the width was 0.006 meters, the inner radius was 0.024, the radius in total was 0.3. The mu, which was found from lab 3, was 3.94. The magnet mass was 0.025 kilograms, and the average time falling through was, of course, 1.47. For the questions related to the experiment, why can't we use a ferrous tube? And this is because it contains iron, and iron contains magnetic properties, which would interfere with the magnet falling. And what happens to the magnet? It falls through the tube slower than it would if it were falling in free space. As for the code itself, you can see that I inputted in all my parameters that I found during the actual experiment, and then from there I was able to calculate what the magnetic force and the flux were on the or what the magnetic field rather was on the magnet itself, and from there able to use that to find what my magnetic flux was, and from there be able to calculate the velocity as it goes down the tube. For the results, using my mu equals 3.94, which is my expected value, I got that the magnet fell through in 0.868 seconds, which was definitely incorrect. So, and just changing my mu value and just playing around with it, I got that if I put my mu as 5.2, it equaled a value that was closer to my expected value. For the glow script questions, which color corresponds to clockwise/counterclockwise current? By using Lenz's law, red is counterclockwise and blue is clockwise. What happens if you flip the magnet? The magnet would fall as before, but the current directions would be flipped. How does real world delta T compare to computational? Computational is slightly shorter. Accounting for air resistance and human errors can improve accuracy. And then what does the plot shape tell you about the forces acting on the magnet? The gravitational force is greater when entering and exiting the tube, but it's equal in the middle, as you can see. Oh, it won't let me go back. Yeah. All right, some errors in the data. We have some measurement errors, so the stopwatch might have not been started and stopped at the correct times, and then friction force between the sides of the tube and the magnet, and then of course air resistance because we're treating this in a real environment. Post-lab questions, the what if question. What if the tube resistivity was close to 0? How would the magnet dynamics change? From Ohm's law, decreasing the resistance would increase the induced current, producing a stronger opposing magnetic field and slowing down the magnet even more. And then what if the slots were cut into the tube? How would this affect the ring currents model? There would be less current rings within the tube, overall producing a weaker opposing magnetic field and causing the magnet to fall faster. Thank you for your time, and I hope you have a good rest of your day.